Hi, this is Dr. Jana and you are watching video with me on artificial neural network, and specifically we are going for the radial basis function neural network. This radial basis function neural network, it is so important because of its application and because of its universal approximation and so many other things. So in this video lecture we will be covering about this radial basis function and what are the different type of architecture of these things and what is the training and what are the applications. So these are the things we are going to cover. I hope it will be very useful for all the students who are preparing for their BTech, MTech, as well as who are going for project using this radial basis function neural network. It is fine. So now instead of wasting time, let us cover. First of all, we should have some idea about this radial basis function neural network or the Rbfnn. This radial basis function network, it was formulated by Broomhead and Lowe in 1988. It is not that much of old, it is recent ones. And since radial basis functions have only one hidden layer, the convergence of optimization objective is much faster. You must be following. So one input layer and one output layer and only one hidden layer will be there for this radial basis function. That is the reason the convergence of optimization objective is much faster, because you don't have more number of layers, more number of computations not there. Next thing, these RBF networks have many applications like function approximation, interpolation, classification and time series predictions. So that means almost all things it is covered here. So all these applications serve various industrial interests like stock price prediction, anomaly detection in data, fraud detections in financial transactions, etc. So you can understand nowadays most of the complicated things we are using this radial basis function. Then the Rbfnn is commonly used. It is commonly used type of artificial neural network function approximation problem. For the approximation problem, mostly we use this ANN based networks, right? So these radial basis function networks are distinguished from other neural networks due to their universal approximation. What I told you, that the universal approximation is the best quality of this thing, and it is also faster learning speed. Why? Because more the number of layers, so more the learning, because more number of weight adjustment is required, but here only a single hidden layer is there. And an RBF network, it is a type of feed forward neural network, so it is coming under this feed forward, right? And it is composed of three layers, namely what I told you, the input layer, the hidden layer and the output layer, and each of these layers has different tasks, And a brief description of this RBFN network is presented as follows. The training of the RBF model is terminated once the calculated error reached the desired value like 0.01. That means whatever the error, our job is to reduce the error. Elimination is not possible to reduce. So when it reaches to a value like 0.01, then we can stop terminating, or we can terminate the process, right? And the number of iterations, say for around at 500 iteration, so the error it will be coming around 0.01. At that time we have to terminate, right? So then we see that it is completed. And you see in the training iteration, we see that at least around 500 iterations must be completed for the terminations. And an RBF network with a specific number of nodes, say for example 10, in its hidden layer is chosen, and a Gaussian function is used as the transfer function of these computational units, and depending on this case, it is typically observed that the RBF network required less time to reach the end of the training compared to the MLP. See, if you the multilayer perceptron, the limitation is that the training time is long. Sometimes it takes some weeks and months. So that problem is sorted out here in this radial basis function neural network. So these chosen MLP and RBF networks are later examined in the next chapter. Next video we are going to do all the things. Now let us focus on this Rbfnn. And here the agreement between the model predictions and the experimental observations, here it will be investigated, and the result of the two models will be compared, and the final model is then chosen based on this least computed error, right? Then let us see the design and development. To generate an output, neuron process the input signal through a function, we called it the activation function. Okay, you try to understand. To generate the output, each neuron, here the neuron we call it as a node also, the each neuron process the input signal. What is the input signal? X is the input signal we are giving. What is the function? Phi x is the function, that is e to the power minus in brace x minus mu square by sigma square. So this is the function. That means our input x is passed through this function, and these functions we call it as the activation function. In Rbfn, activation function of hidden neurons is phi x for an input of vector x, and output is produced by the hidden neuron, it will be phi x. Okay. Hidden layer will go for the computations and find this phi x, right? And you can see the diagram here also. One node, you see the activation function what here with the Gaussian function. Here at the center you can see it is there, and it is decreasing. The range is there also limited by these things, and it is decreasing gradually. Once we are going away from the center, these are the basic things we remember. The above figure represents a Gaussian neural activation functions of 1D input x, and the input is x with the center mean is equal to mu. Okay, remember this is the diagram what I have shown. It is a 1D, one dimensional Gaussian function, and here x is the input and mu is the center, or we can say the mean, and here phi x represents the output of the Gaussian node for a given value of x, and it can be clearly seen that the signal strength decreases as the input x moves away from the center. At the center it is maximum. If you see the previous one, at the center it is maximum. If you are going away from the center, both the sides, it is decreasing, right? This is the thing. So the signal strength decreases as the input x moves away from the center, and the range of this Gaussian function is also determined. You can see the range when it is decreasing. You can see it here. So just 1 minute. So at this point we can terminate at this point, here also at this point. So this point to this point will be its range, right? The basic idea of this model is that the entire feature vector space is partitioned by Gaussian neural nodes. Okay, the entire feature vector, because what is the input we represented as a vector. Now the entire feature vector space is partitioned by a Gaussian neural node, where each node generates a signal corresponding to an input. So that means what are the input when it is passed through the Gaussian function, then it generates a output. Understand? Generates a signal corresponding to the input vector, and strength of the signal produced by each neuron depends on the distance between the center. That means if the node is at the center, the Gaussian function is at the center, then the signal strength will be more, and if it is going away, the strength will be decreasing. That we have shown the program, you have understood. Now also for input lying closer to the Euclidean vector space, the output signals that are generated must be similar to phi x, which is equal to e to the power minus that is x minus mu square divided by sigma square. This is the function you have to, mathematical function you have to remember. Here mu is the center of the neuron, phi x is the response to the input x. Okay, and here mu is the center of the neuron and phi x is the response. Okay, what I told you, the same thing repeated twice. Now you can see the diagram. This diagram is just enlarged one. I will show in the next page. Just you try to understand here. In the above figure, the different circles are there. These circles represent the Gaussian neural nodes, and boundary of the circles represent the range. See, we are talking about the range, no? So that means this function is covering within the periphery. Okay, and the strength is maximum at the center. That is meaning. And the range you can see the boundary, where the boundary it is there, up to that boundary it is range, right? So now boundary of the circle, it represents the range of the corresponding nodes. This is also known as the receptive field of the neuron. That means receptive means up to that it can receive the information. Here 2D vector space is partitioned by 12 number of Gaussian nodes. So you can see the first layer 1, 2, 3, 4, second layer 4, 4, 4. It is 12. Okay, so 12 number of nodes are there. The entire space is partitioned by 12 number of Gaussian nodes, and every input vector activates the collective neuron system of the neurons to some extent, and the combination of these activation enables Rbfnn radial basis to decide how to respond, and above configurations of neurons will be generated, generating similar output signal for input vectors A and B, where you see where is what is A and B. See here, you see this is the center, A and B closer to that one. So A, B will be producing similar type of things, but C is away from this one, so C will be producing something different. That is the thing she is explaining. Okay, so because A and B are closer to this node and this radial basis function, okay, because this is the center, but C is away from that one. That's why A, B will be similar, C will be different, right? Then in the radial basis functions architecture, weights connecting input vector to hidden neurons represent the center of the corresponding neurons. What is the meaning of that one? Weight will be there from input to the hidden and from hidden to the output. Okay, now we are talking about the weights connecting input to the hidden neurons. It represents the center of the representing neurons. I remember that one. These weights are predetermined in such a way that the entire space is covered by the receptive fields. I told you that 12 number of things you have taken, it is covering the entire space, right? Whereas values of the weights connecting hidden neurons to the output neurons are determined to train the network. So, two type of things are there, you have to remember. So, this you can see x to phi x. So, this is just like you can see this is the input to the hidden, and phi x to c, this is the hidden to the output. The same thing what I told, it is explained in this figure. Now, it is appropriate if vectors lying close to Euclidean space falls under the receptive field of the same neuron. See, the one node what I represented by the circle, they are one node. If this Euclidean distance, that is AB what I have given, it is closer to the same node, then only you get it now. So, it is appropriate if vectors lying close to the Euclidean space falling under the receptive field of the same neurons. Therefore, center of hidden neurons are determined using the k-mean clustering. K-mean clustering, it is also one type of algorithm we are using for the unsupervised type of training. So, I have a video on these things, you can refer there on. So, here we call it the k-mean clustering algorithm, and here we choose the number of cluster centers k. That means, suppose in a graph, in a 2D graph, it is given the number of points or the data sets are given. So, we arbitrarily select 3 or 4 points there, and we see what are the nodes closer to that point. This point k, whatever we select, we call the centroid, and what are the nodes closer to that one, that you check out on that one, based on that you go for the clustering, right. So, this is the main principle. Randomly choose k points from the data set and set them as k centroids of the data, and for all the points in the data set determine the centroid closer to that one. So, what are the points closer to that centroid you determine and they group them on. For all centroids, calculate the average of all the points lying closer to the same centroid. That means, same point may be closer to x1, closer to x2 or x3. So, who are the things closer to x1, they are coming under x1. Who are closer to x2, they will be coming under x2, like that, that's all. So, change the value of all the centroids to corresponding average calculated in 4 and go to the 3 until. So, this is the steps we have to follow. Now, the range of the receptive fields is chosen such that entire domain of input vector is covered by the receptive field of the neurons. You have seen that figure where I have shown 12 number of nodes, it is covering the entire space, and we have to select in such a way that the entire area or the entire input vector is covered by the receptive field. Okay. So, the value of the sigma is chosen accordingly to the maximum distance between. Then for that we need sigma. Then how do we decide this sigma? The sigma is selected which by the formula sigma is equal to d divided by square root of twice m. M is the number of hidden neurons, not layer, hidden neurons, and because there is only one layer, number of neurons is m, and d the maximum distance, Euclidean distance, and we calculate the sigma based on d divided by square root of twice of m, right. So, then what we do, it is used for approximations and recognitions pattern recognition. It uses a Gaussian function, and it is a multi-layer feed-forward network within a input neuron. Suppose m is the output neuron and one hidden layer in between. Input to the hidden is hypothetical connections, hidden to the output vector are connected. Now, what is the activation function? Activation function clearly getting a Gaussian function, is represented by fx is equal to e to the power minus of x minus mu square by sigma square. And here for sigma greater than 0 and x and c, whatever things you are telling, they belongs to the set R. Okay. If you go the first order derivative of that one, f dash of x, so because x square minus x square is equal to, there is minus twice of x, again e to the power minus x, right. This is the differentiation, you know, that is equivalent to minus 2x of fx. So, this is a clearly mathematical background is there. Then coming to the architecture of this Rbfnn. Rbfnn network is an architectural neural network with an input layer, a hidden layer and the output layer. The hidden layer of Rbfnn consists of hidden neurons, and the activation functions of these neurons is a Gaussian function. Okay. So, one is input layer, it is only carry forward, no work. Output layer, it is giving the output. The hidden layer only going for all this processing, and in these hidden layers every neuron it is having a activation function that is called the Gaussian function. That is the meaning of these things. Now the hidden layer generates a signal corresponding to an input vector in the input layer, and corresponding to the signal network generates a response. So this is the thing. Now you can see there. Now you can tell me where is this activation function? This activation function is here in the hidden layers only. It is hyperbolic function. E to the power minus something I tell you no. So Rbfnn was originally introduced for interpolation of data points on the finite training set. So now f of xk, that is the dk is the desired output, f xk is the input, and when xk is processed by the function activation function f, then we get the desired output k. Okay. Now for interpolations of Rbfnn, it assumes the set of basis functions. Now what is that? Q is equal to phi of x minus xi. What is x? So suppose x is the centroid. We have selected k, no? We selected one center x, and xi all other points closer to that one. Okay, is that. To train the points, what we do? F of x is equal to wi into phi of xi and plus w0. W0 is the bias. Okay. So this is just like the training, you can understand. So wi is multiplied with x. Here x means the distance between centroid and other points in the data set. Okay. And how many centroid will be there? Because according to the we have taken k number of things here, because the k means, so k number centroid will be there. Okay. So k is equal to 1 to something like that, I put it there. And the Gaussian function is represented by this one. Now w0 is the bias, where I told you that, and xc belongs to r. Now example, let noise data of q is equal to 10 data points scattered of a function. Say function is given 2 sin x plus x. Okay. Then we calculate phi of x minus xi using this formula, center at that point x. Now a Gaussian function is generated using this value, and ki the covariance matrices, what I told you that it spreads of sigma is 0.5 to 1.0, and this is the covariance matrix. It is 5 and 10, and as the spread increases, the approximation becomes smoother, right? So this is the thing. Then you can have the mathematical development for the training. So because we are having two type of weight adjustment here, let Gij be the element of the matrix G representing the output of the jth neuron. Okay. So final output jth neuron. So it is represented by my matrix G, and the individual things are the Gij, right? The input vectors j and the input vectors, and so this Gij the input vector, and Wij be the element of the matrix W represent the weights. Okay, one is the input, one is the weight. Okay. In Rbfnn, the activation functions of the output neuron is linear. For the output is linear, remember. So that is g of z, which is equal to z, where z is the weighted summation of this. It is the same thing what we are using for our perceptron, same thing we are doing. So one is input x, one is w, x into w, it is net, it is processed by function, same thing, only different rotations it is given here. Then multiplying the ith row of g with the jth column of w does the weighted summation of the standard. Okay. So these are things. Then we got it, one is the g and one is the w, and g into w, this we altogether call it the t. What is the net in the previous cases? Okay, t is the column vector and all the things. Okay, and it is to be processed by that function. Okay, what is the algorithm? Define the number of hidden neurons, that is k. Set the positions of RBF centers using k-mean clustering. Calculate the sigma using the equation number 2. Sigma is equal to, I already given how to calculate sigma. And calculate actions of Rbfn node using the equation number 1. Train the output using the equation number. So these are the things it is there. So I think this is enough to have some idea about this Rbfnn. I will be skipping the part of this RBF versus the MLP in some other videos. Will be going for that one. I think this we can go for this linear separability. Clearly you can go for this separability, the exclusive bar problem, all things we can do it here. So if you want, I will show you also. Now let us go for the training of this Rbfnn. First we should train the hidden layers using backpropagation. See, remember, the hidden layers are trained using the backpropagation, and the neural network training backpropagation is a curve fitting method, and it fits a nonlinear curve during the training phase, and it runs through the stochastic. You see, one is the linear, one is the linear means represented by a straight line, y is equal to ms plus c, but it is not necessary that always it will be just in a straight line. So that's why it is just like a, you have to, it can be non-linear curve, and the fit a non-linear curve, that is the job there, it is done. Okay, during the training phase we are going for the fit a non-linear curve, and it runs through stochastic approximation, which we call it the backpropagation. For each of the node in the hidden layers, we have to find T, the receptors, and the variance sigma. Okay, and on the second training phase, we have to update the weighted vectors between the hidden layer and the output layer. One is the input to hidden, and that is the hidden to the output layer. In the second phase, we are adjusting the weight between, or updating the weights between the hidden layer and the output layers. On hidden layer, each node represent each transformation basis function, and any of the functions could satisfy the nonlinear separability, or even combination of the set function also can satisfy. So this is the training principle. So in our hidden layer transformations, all the nonlinearity terms are included. Say for example, I am taking say x square plus y square plus 5xy. So this is not a linear function, because you can see it is some x square is there, y square there, it is not a linear function. So it's all included in a hypersurface equivalent to x and y are input. Therefore, the first stage of training is done by clustering algorithm. We define the number of cluster centers we need, and by clustering algorithm we compute the clustering centers, which then is assigned as the receptors for each of these hidden neurons. And we have to cluster n number of samples, that is if okay, and this n must be greater than m. Okay, n samples are observations into m clusters. Okay, so the sample is more, cluster is less. Okay, n number of sample, cluster is m. So the output clusters are the receptors. Fine. So this is the thing. For each receptors, we can find the variance as the square sum, because there is a formula for that one, 1 by n, that is square of x minus t. Okay, so from this, x is the input center, you can understand, t the receptor you understand, and 1 by n is the number of things. The interpretations of the first training phases is that the feature vector is projected into the transform space. Now this is the diagrammatical things it is given. What are the advantages using the Rbfnn over the MLP? Training of Rbfnn is faster, as I told you that only single layer there, but multi-layer perceptron, it takes many iterations and long time. We can easily interpret, that is the meaning, function of the each node is hidden layer of the Rbfn. This is difficult for MLP. And what should be the number of nodes in hidden layer and the hidden layers in the multi-layer perceptron? Okay. This parameterization is difficult for MLP. We can decide in case of hidden layer, but in multi-layer perceptron it is difficult. So classification will take more time in Rbfn than the MLP. Only the thing is that classification it takes some more time, because we don't know the output in advance, because it is unsupervised table training. Then the learning algorithm, we train the hidden layers with unsupervised learning algorithm, and train the output layer with a supervised learning, and simultaneously apply a supervised learning algorithm to the hidden and output layers to fine tune the network. This is the thing. Then this is the learning of the Rbfnn. Suppose we are going for a solving one exclusive problem. So here we know exclusive problem, when both the inputs are opposite, then only output is equal to 1, other cases it is 0. So in that case it will be difficult to have a linear separability. So for that, what we do, we represent the function as w0 the bias plus w1. So it is where all this is the thing. So d are represented as the things 0 1 0 0, and w is equal to w0 w1 w2, all the things I have given it. Okay, w3 up to w3. Okay, so then from this the function is represented as pi. Here it is represented by this function. How do you get this function? Because we apply the equation using the value of the input d and w to get this function. Now this is the phi function, we got it. Phi is equal to e to the power minus, already I told you. So then you applying the value of x and t, we can get this phi, and transpose of phi also you can get it like this, right? So once you get all the things, the final weight adjustment it is like this. Okay, what are the application of this Rbfnn? The application of this neural network is a number of fields. The signal processing like equalizations, echo cancellations, data processing, voice and image, communication systems, traffic flow control, switching, and controllers in the robotic movement, all the things it is done there. Other applications, classification of aircraft radar signal, automatic target recognitions, real-time process visualizations, forecasting of solar activities, loan eligibility predictions, credit card fraud detection, stock market prediction, domestic applications. So these are the things we come across, and I hope you got a very clear concept on this radial basis function. And if you have any doubt or queries, you can SMS to me, or you can write a mail to me also. I hope you enjoyed this video. If you really like this video, please do share with your friends, and also don't forget to subscribe this channel. Thank you for watching this video. Please take care of your health.